Hello, Physics 10. I'm actually back in the lab for a short period of time, and I wanted to talk about the next section right here. It was actually on temperature and heat, right here. And let me first talk about temperature. Well, what is temperature? And we know it's something that we know when something feels hot or cold, we have some measure with our hand of temperature. And we also know that if something gets, like water gets really cold, it'll freeze. And it always freezes at the same, what we'll call temperature right here. We can also say things, certain materials expand and contract when you heat or cool it down. And so something like a thermometer, if we look at a thermometer right here, just look at a mercury thermometer right there. Mercury, it expands when it gets hotter and hotter, and so if we have mercury in here and it expands, it's just going to go up the tube right here. And we can define a specific temperature where freezing occurs. Let's just call this the freezing point. Freezing point. It's a nice specific temperature right here. We could also look at the boiling temperature right here. Now, when we're talking about boiling, it depends on the pressure. So when I say boiling, I mean at sea level. So let's just say that is the boiling point. Boiling point. Now, we can assign a number to these two values. It doesn't matter right here which one we pick. And if we look at the first scale that came out, which was the Fahrenheit scale, which is the scale that we use here in the United States for most of our measurements, the freezing point they had set at 32 Fahrenheit, 32 degrees Fahrenheit, and the boiling point was 212, crazy numbers right here. And now, if we would just put this in room temperature right here, room temperature, it's somewhere in between here. We're actually closer to the bottom right here. Room temperature is, so this is normal room temperature, somewhere in the, say, 70 degree Fahrenheit range right there. Now, this is kind of a strange scale, and Celsius says, I can think of a better scale than this. Instead of being 32 and 212, maybe it's better if we change that. Instead of 32 and 212, let's just make it a nice even 0 and 100 right here. So if we just turn this to 0 degrees, now it's Celsius, and this one up here is 100 degrees Celsius. All we're doing is we're just changing what we're calling the scale right here. Now, you'll notice that there's almost 200 degrees between here and here. Over here, there's only 100 degrees. So 1 degree change in Celsius is like 2 degree change here. Now, you notice the weather in the United States, they never give it to you in Celsius. Every other place they do. Why don't we do it here? Well, whereas normal at 70 degrees would be somewhere around, say, 23 degrees Celsius. You notice when it gets really hot in here, we get up to what? 100 degrees Fahrenheit. The news loves that because then they get to use the word triple digit. And it's dramatic right here. Here, and if it's 100 degrees, it's like 40 degrees or something. And, it just doesn't have the dramatics that this has. So the news loves the dramatics right there. So that's the reason why I think we use the Fahrenheit instead of the Celsius right there. Well, suppose we have these two scales. Let's say I have an object. I don't know, it can be a block of some material, steel or something. And let's just say it's 10 degrees Celsius right here. Now let's make it twice as hot. Twice as hot. What is the temperature here? Right here. Is it 20 degrees or is it something else right here? How about if it was 0 degrees Celsius and we made it twice as hot? What would it be over here? If you double it, it would still be 0. Well, it can't be 0 if you're making it twice as hot. That's the same temperature. Not only that, what if this were minus 10 degrees Celsius and we made it twice as hot? Well, it certainly isn't going to be minus 20. That's even colder right here. So you notice you have a problem right here when you just want to say something is twice as hot right here. Well, the reason why you have the problem is because you have a scale that goes negative right here. And if you make this guy twice as big, he's even going to be more negative right here. So if we ever want to use a scale like this, we'd like to have one that never goes negative. And so Kelvin says, Kelvin said that the temperature is somehow related to the speed of the molecules right here. Well, there is a minimum speed for the molecules. It's 0 right here. You can't go up a negative speed right here. And so he said, why don't we call 0 speed of the atoms, why don't we call that 0 degrees in Kelvin scale? So what we have is we have a third scale right here, which is the Kelvin scale right here. So this is Celsius. Is Fahrenheit, I'm not going to spell that out. And this is Kelvin. Well, this is the coldest possible temperature here in this scale right here, way down there, is minus 273 right here. This one is like minus 450 something. I don't know if it's exactly that, but it's somewhere in that range. So what Kelvin says is let's just take this scale and shift it down so that this is 0 degrees Kelvin. And if I shifted everything down by 273, this would be 273 Kelvin. This up here, if we just shifted it down by, that would be 373 Kelvin right there. Okay, so in room temperature right here would be like 296 Kelvin. You notice we'd never use that in the news because they'd say, oh, it's a mild day of 296 Kelvin. But that 305 would be really hot. There's just there's no dramatics for that either right there. Okay, so now if we're going to use this technique right here, we really have to use this scale over there. And so 10 degrees Celsius right here is really 283. So this is really 283 Kelvin. So if I was going to double it, I'd have to double the 283. That's 566. This is 566 Kelvin. And if I wanted to know what that was in Celsius, I would subtract 273. Subtract your 273. What does that give you? It gives you 3. 16 minus 7 is 9 from 293 Celsius right here. This one right here, I'd have to move it over to 273. That's what it is in Kelvin. Double that, that's 546. Then to put it back into Celsius, subtract the 273. And so that's 273. 273 Celsius. Okay, well, you notice this. This is the temperature of ice. This is the temperature of fire. You notice if you double the temperature of ice, you get the temperature of fire. So you could just say ice is half the temperature of fire. Boy, doesn't seem that way, but it is. So ice is pretty hot. It's half the temperature of fire right here. Minus 10 degrees, you would do the same thing right here. This would be 263 Kelvin. And then you double that, that'd be 526. And then you subtract off the 273 to put it back into Celsius right here. And that's 253. That's still hot right there. So remember, 100 degrees Celsius is boiling water. This is hot right here. It's 3 times the temperature of boiling water. So ice is, you know, we might not think it's a high temperature, but it is. It just feels cold to us right there. Okay. So now we have some way of measuring the temperature. It's a measure of how fast the atoms are going right here. And so what Kelvin said is he said, you have some atoms here moving around in some container. It could be gas atoms, water, whatever you have right here. Let's just make them gas atoms. Maybe it's a helium in a tank or something right here, and you got these atoms jumping around. Each one of these has a velocity, v1, v2, v3, and each one has a kinetic energy. Remember, we said the kinetic energy was 1/2 mv squared. Now, if we were to find the average of all these kinetic energies, how do we do that? We add them all up and divide by how many there are. The average 1/2 mv squared, because they're not all going at the same speed. Some are going a little faster, some are going a little slower, right here, because they're bumping around. The average of all this is related to the temperature. It's actually equal to 3/2, some constant, not that constant, it just happens to have the same letter. It's called Boltzmann's constant. Boltzmann's constant. The value is around 10 to the minus 23, right there, it's a pretty small number, times the temperature, but that's in Kelvin. In Kelvin. Right here. So we can see at 0 degrees Kelvin, they've stopped all the motion right here. This can never go negative, so you can never have a negative temperature right there. So if I wanted to find out what the temperature of, say the speed of the air molecules in this room are, I know what that number is. The temperature in this room is somewhere around right there. We could just use 300 right there. So you know the K, you know the temperature, you know what the mass is of the air atoms, and so you could find out what that average speed is. So solving for that average speed, you could cancel the m's. So you cancel the m's, you got m times the average speed squared is 3 kT, or v, divide out the m and then take the square root. So you got the square root of 3 kT all over m. So all you have to do is plug in the mass of, well, what's air? Air is mostly nitrogen, N2. And they know the mass of that. They know that number. They know that. You can calculate the speed. And the speed of the air in this room is probably a little bit faster than the speed of sound right here. My guess is it's going to be around, say, 800 miles per hour. You notice that's pretty fast, and yet it doesn't even mess up your hair right here. The reason why it doesn't mess up your hair is because it's not a wind. They're all coming at you at different directions, and so it just kind of bumps you, pushes you right here, but it doesn't mess up your hair. Now, if all the air atoms were going that speed and in the same direction, yeah, you'd be flying off right there. So even if you put in ice in here, the speed of ice atoms, you're still going to put in 273 because you're in Kelvin. Ice is 273. Even ice is going, the molecules are still moving around pretty fast right there. So, okay, so there is temperature right there. And you notice if we have a hot object right here. Let's say this is hot, and we may say a piece of steel or something, and we put it in contact with something that's cold right here. Here the atoms are moving around fast, here they're moving slow. When these atoms, fast atoms, run into slow ones, it's going to slow these down, it's going to speed these up. So this is going to slowly get warmer, this is going to slowly get cooler, and so you've got something, the kinetic energy of these guys is somehow moving this way right here. So this energy is being transferred from the hotter down to the colder, and we call that transfer of energy, we call that heat. That's what heat is. Heat is the transfer from the hot object to the colder object right there. Okay, so, and if we're going to want to go the other way, we have to put in a lot of our own effort. That's what a refrigerator does. We have to plug it in and push the heat away from the cold right here. Normally it wants to go this way by itself right there. Okay, well, we said what the coldest possible temperature. What's the hottest possible temperature from this? Well, actually, what about the temperature of outer space? What's the temperature of outer space? If you've seen Apollo 13, you notice it gets pretty cold out there. Well, that's for a different reason. But if I were to take a little block of steel and put it up into space and say, is that going to get hot or cold? Well, it all depends. If you put it in the sun, it's going to get hot. If it's in the shade, it's going to get cold right here. The reason why it didn't get hot in Apollo 13 is because the spacecraft was reflective, and it just reflected all the light from the sun that hit it right there. But what is the temperature of outer space? Well, what's the average kinetic energy? Well, if you have a perfect vacuum, there are no atoms right here. Well, what's the average of zeros and zeros and zeros? Well, what do? You add them up and divide by how many there are. Well, if you add them up, you get 0. You divide by 0, doesn't make any sense right here. So the temperature in a vacuum doesn't make any sense. If I put something in the vacuum and measure the temperature of that, well, it's all going to depend on whether it's in the sun or not. If you were to take the sun away, take the sun completely away right here, this thing right here would eventually become, this thing would be about 3 degrees Kelvin, which is pretty low. Remember, 3 degrees is way down here someplace right there. So that is the temperature of deep space right there. So it is awfully cold out there in deep space right there. Now, what about if we heat up a material right here? So let's just say we have some material right here and we heat it up. And what does this thing do? This thing raises the temperature right here. Now, we'll notice that certain things heat up very easily. Some things are hard to heat up. I don't know if you've ever watched water boil, but you can't. You put it on the stove and then you got to leave and wait for the whistle on the teapot to happen. Water is a very hard thing to heat up. Certain things are very easy. A block of steel heats up pretty easily right here. So this measure of how hard it is to heat up something or how much to cool it down, we call it specific heat. Specific heat. We give it the letter C for specific. Well, and it just tells you how many units of energy, well, which we call joules right here. Usually, when we're dealing with heat, we don't use joules. We use the other unit, which is the calories. It says how many calories of energy I have to give it to raise 1 gram of this substance, 1 gram, 1 degree Celsius. 1 degree Celsius. And that's what the measure of the specific heat is. And we define the calorie as how much it takes for 1 gram to go 1 degree Celsius. So C for water, H2O, is defined as 1. That's where we got the calorie from. It's 1 calorie per gram degree Celsius right here. That's a big value right here. Certain values like steel, much lower than that right here. There's certain foods that are hard to heat up. Potato, you don't just put that in the oven for a few seconds. You got to keep that in the oven for a long time right here. Potatoes have a pretty high specific heat right there. Okay, so that's a measure of the specific heat. And so if you wanted to figure out how many calories it took to make that hot cup of coffee in the morning, what do? You have a glass of water. Let's just say it's a liter. That's 1,000 grams of water. That's 1 liter. And let's say you go from room temperature from 25, let's just go from 25 degrees Celsius all the way up to boiling, 100, degrees Celsius. And you say, how much energy does that take? Well, 1 calorie to move 1 gram, forget about the 1,000, to move 1 gram from 25 to 100, we need 1 calorie for each degree Celsius, so we need 75 calories for each gram. Well, we got 1,000 grams, so it's going to be 75,000 calories of energy it takes to make that cup of coffee. If we wanted to convert that into joules, because we looked at joules before in class, we multiplied it by 4, and now we're in joules. And that would be 300,000 joules. And that's, I'm trying to think, when we looked at electrical energy, it was somewhere on this order per penny right here. So, it might cost you a penny to make that cup of coffee. Probably more because you're probably wasting a lot to the rest of the kitchen and stuff like that. But on the order of a penny, a few pennies right there. Okay, well, water, why does water have such a high specific heat? And why does steel have a low specific heat right there? Well, I'm going to come back to right here. It's because if we look at water, water is H2O. Here's the O, and here's the 2 H's right there. H and O. Think of them like little springs in there. Now, when you start to heat up water, some of this energy can go into just moving this around, into kinetic energy. So some of it goes into kinetic energy. Kinetic energy. But some of it can go into vibration. You're going to make these little springs that are holding these on move around better. So some of it can go into just shaking, well, let's just say harmonic motion, or we can just say just shaking the springs, or vibration. Vibration, but that's better. To vibration. And some of it can go into spinning this, into rotation. Rotation. So there's just these 3 that it can go into right here. Now, it just so happens there's a rule in heat and thermodynamics that says it shares evenly. So whatever you put into here, energy, 1/3 of it will go into this, 1/3 of it will go into that, and 1/3 of it will go into that. This is the only one that makes it hotter right here. These don't make it hotter right here. So as I pump in energy into water, only 1/3 of the energy goes into making it hotter. The rest of them go into making it shake more and spin more right here. So that's why I have to pump in so much. If we look at steel, steel doesn't have these 2 states. So it's, when I pump in, it all goes into there. Now, is that a good thing or a bad thing for water? Well, it's actually a good thing, because if it's hard to heat up water, then it's also hard to cool back down. Because now, let's say you've heated up and now all these have energy, and now it starts to cool and this one starts to get smaller. Well, when he gets below these 2, they help out and they share. So now water will stay hot much longer. If we didn't have these 2 other states, you would never drink hot coffee. As soon as you pulled it off the oven, it would be cold right here, right away. So you wouldn't even bother heating it up. So we're lucky that it has these 2 extra states right here. Anything that's hard to heat up and hard to cool down will have these multiple states right here. Now, if we look at something like a microwave oven, what do? They pump in a whole bunch of energy with microwaves, but that puts it all into this one. All the microwaves go into just spinning these atoms. All they do is they just spin these. So these things, all the energy is pumped right into there. Let's say you pump in, 100 joules. Let's say 300 joules. You pump in 300 joules into there. that's not going to raise the temperature right here. This is what raises the temperature. So you notice what they always tell you to do is to not pull it out of the microwave and throw it in your mouth. They say let it sit for a while. Why? So that this guy can share his energy with these two. So he'll share 100 with this and 100 with that, and pretty soon they'll all have 100, and this will be warmed up right here. You don't want this sharing going on in your stomach. Right here. You'd rather have it already share right here by the time you eat it right there. So that's what microwaves do. They just spin the water atoms right here. And so you don't want to put that dry turkey in there because you want water molecules. Anything that has it's just completely dry might not even heat up right there. This thing is really good for spinning water molecules. You notice you don't want to put metal in there because metal doesn't have these two states, and so when you try to pump in all that energy, you can get sparks going, especially if you have don't put steel wool or something, anything with a sharp edge to it right there. So a microwave pumps in all in there and then it shares right here. If you've ever seen a heat lamp, they always have them at the supermarket pointing down at chickens or something like that, the cooked chickens. They're pumping it into here and they put it into vibration, then it shares right here. Regular ovens are in this one right here. So there's looks like we have three types of ovens. You can either microwave, heat lamp, or just a regular heating element right there. So, because water is so hard to heat up, that affects temperatures around the world. It has such a high specific heat. If I were to draw the United States here, there's Florida and Texas right here. What do we have? We have a big ocean over here. Ocean. This has a very high specific heat right here, which means the temperature doesn't vary much right here. Whereas dirt has a low specific heat. This temperature on this can get really hot and really cold. You probably notice that even at the beach in the middle of the day, the sand gets really hot. At night, the sand gets cold, but the ocean temperature really doesn't change at all day and night right there. Okay, so now we have winds that blow in. The winds always blow in from us. They always blow toward the east right there. So here's the way the air currents blow right here. So now you got this big source of object that never changes its temperature. So if you go down to the beach, the temperature of the air doesn't change that much year round right here, or even in Riverside it doesn't change that much. If we were to go straight across from Riverside over to this part, or even in the middle of the United States, they get snow all the time over here. We don't really get snow because we've got this big source of heat blowing air in over here, unless you're up in the mountains right here. But down here at sea level, we're never going to get snow along this coast right here. Florida right here, normally they never get snow unless the winds come in that direction. Then they can get snow right there. You can only get snow when the air blows over something that has a low specific heat like dirt right there. If we look at Hawaii's out here, no matter which way the winds are blowing, the temperature doesn't change that much right here. And the temperature on Hawaii only changes a few degrees in the whole year because it's blowing across the ocean no matter which way. If we come over here to Europe's a little harder to draw right here. I'll draw it like this. So there's Italy and there's Spain right there. The winds blow like this right here. So it's going to be a little bit milder over here. They're pretty far north, so it's going to get pretty cold right there, but it's still milder. Over here, it's really harsh right here. Siberia and places like that right there. If we look over here, we have Iceland. And next to it, we have Greenland. Greenland sounds nice. Iceland sounds terrible right here. The only thing is, if you go to Iceland, that's green, and if you go to Greenland, that's ice right here. The reason why they call this ice Greenland and not Greenland is to keep people from coming. No one wants to go to a place called Iceland. Everyone wants to go to a place called Greenland. But Iceland even though it's far north, it's still an island, and the temperatures are going to be much more milder than if you're part where the winds are blowing over the continent right there. So just from global wind patterns, you can kind of tell what the temperature is going to be like right here. Now, when water is kind of a strange element right here. When you heat up water, it expands, and when you cool it down, it expands. It expands both ways right here. Most materials, if this is the temperature, and this is the volume, like a piece of metal, most metals, as you heat them up, they expand right here. So this is what you get for most metals, or almost any substance. It all goes like this right here. Things expand when they heat up, they get smaller when you cool them down. But water's kind of special. Water, it looks like it does expand right here, but then it gets to a certain point and then it heads back up right there. And let's just say right here is 0 degrees Celsius. So all of a sudden it turns into ice. When it turns into ice, it really jumps right here. But around 4 degrees Celsius is where water is at its densest point right here. The reason why is because you're starting to create crystals already. So it normally would keep coming down, but you're starting to form crystals. If you looked at our water molecule, what does it look like? Looks like the two hydrogens and the oxygen, and they're connected to 2 more, they're connected to 2 more, connected to 2 more, and so on. And so you notice when they form kind of like a little ring, and you got a void in the middle. So when you start to crystallize, you've created these little voids, and that gives you little air gaps in there, and that's why it starts to expand. And it's going to start before 0 degrees. It's going to start over here, and so it starts to head back up. So water's at its densest point at 4 degrees Celsius. So if I asked you what's the temperature of the bottom of Lake Tahoe all year round, it's probably 4 degrees, because that's a deep lake and all the heavy water is going to go to the bottom right here. So now, is this a good thing or a bad thing for ponds that they float, that the heaviest water is at 4 degrees? Well, suppose we have a pond right here. Here's a pond. We got some water in it, and let's say it's liquid. It's all water in here. Let's say it's 10 degrees Celsius, and let's say all of a sudden the air temperature became minus 10 degrees Celsius. Well, what's going to happen? The water surface will start to lower in temperature. It'll get to 9 degrees. Well, you notice here's 9 degrees, and here's 10 degrees. 9 degrees is denser, so 9 degree drops, 10 degree water fills in. Pretty soon this whole thing is at 9 degrees, then 8 degrees, 7 degrees, and again, the colder water will keep dropping until the whole thing gets down to 4 degrees Celsius. Now, when you're at 4 degrees, 3 degrees won't sink because you're starting to go back up. So 3 degrees will stay at the surface, 2 degrees will stay at the surface, 1, and then this freezes right there. You freeze the surface. You just get ice layer just on the top. Ice we'll see is a very good insulator, which protects this from getting any colder right here. So if you have some fish down here, you don't want him getting frozen solid in there. He can still swim around. They're still liquid. You've insulated yourself. That's what this ice is. It's a good insulation right here. Insulates the rest of the lake right here. So I guess it's a good thing right there. Otherwise it'd be tough to ice fish. You'd have to dig out the fish out of the ice right there. Now, we did say that since objects expands, like metal expands when you heat it up, so if I have a stick, a metal pipe, or let's say a metal rod right here, and I heat it up, it's going to get longer right here. I could use it as a thermometer if I wanted to. It just gets longer right there. It gets wider too, but not much right here. Well, what if we have a ring? Well, actually, what if we have a plate of steel, and we put a hole in the plate of steel, and we heat up the plate? What happens to the size of the hole right here? Well, if you ever want to know what's going to happen to the hole, look at the piece that you cut out. Here is the piece that I cut out. There's the piece that used to be in there. If I heat up this piece will get bigger. This will do exactly the same thing that the piece I cut out did. So the hole will get bigger if you heat up this plate right there. If we have a ring, let's look at a ring, a ring right here. And now we heat it up. Does the inner part of the ring get bigger or smaller? Well, just look at the inner piece right here. This piece that you cut out in the inside. If you heat up that's definitely going to get bigger, so the ring gets bigger right there. What if we cut a notch in it? Cut a little notch right there in the ring. Now we heat it up. What happens to the size of that little piece we cut out right here? Well, that piece we cut out is right here. If I heat up this piece gets bigger, so this gets bigger. If you ever want to know what happens to the gap, look at the piece you cut out and heat that up. It's going to do the exact same thing. So the gap and the piece are exactly the same thing right here. Okay, and so I think that covers at least the heat right there. And the next one we'll see how we can transfer this from one object to another, this internal energy or this heat right there. So.